I'm giving you the derivation here, but I want to use your intuition with this equation. I claim that if I collect n data from this distribution, I want to write the likelihood model, which is the probability of all of this data given x. And rather than writing the probability of y1, y2, yn, I am writing the probability of the sample mean of y given x. Because, you know, you can think about it, that would be sufficient statistic for what we want to do. That's enough information from the data, okay? You don't need anything else. And I claim here that the probability of the sample mean of y given x, it is x times 1 over n times the covariance sigma y. Okay? If you don't believe me about this derivation, I actually give you the proof on this asterisk, so I want you to read it. So I don't complete the square, but I look at this expression and visually immediately you can recognize that this is correct. Now, why I like this trick? Because look what happens. Now forget the fact that you had this many data points. I only have one data point, all right? And that data point is called y bar, all right? So this is my likelihood. This is my prior. And notice something interesting. The likelihood, the mean, is a linear function of x. So it's like having a conditional of y bar given x and a prior on x, which is Gaussian. So this fits hand by hand with what? With the linear Gaussian models that we discussed before. Can you see that? I have a prior on x, and then I have a condition of y given x, which is a linear model because the mean is x. So before, you remember we had ax plus b, so a is identity, and b is 0. So if you take the results that we had before and this complicated formula, all right, you can directly plug in, and there is the posterior of x without any calculations. All right, so don't spend time and say, oh, this is, you give us too much homework, because at the end of the day, when you learn these tricks, you can actually do this directly in one line without having to do these calculations. And let me see, I'm going to give you one example to finish, okay? Another example. So we had, you know, a likelihood that it's Gaussian, a prior that is Gaussian. So let's say that we are trying to measure the mean mu of the Gaussian distribution, right? But we have two sensors, so we collect two data points, but the two data points come from two sensors that each of them has its own variance. So before, you remember, the data come from the same Gaussian, but now one of the data points comes from a Gaussian that has this variance here. Another point comes from another sensor, has another variance. Here they are equal, basically, but basically one says the mean is there, the other one says the mean is there. So obviously, if you form the posterior, you know, you will get effectively a posterior that gives you an estimate somewhere in between, and this is the variant of the posterior. Okay? And by the way, my prior model, just to make the case here, it says that the mean is around 0 and the variance is huge. So I don't basically want to have to deal even with a prior model. So the variance here is huge, is not going to dominate the problem. But what I wanted to show you is the following. Suppose the likelihood, the two sensors come from two Gaussians that have a different behavior. So for example, let's concentrate on this picture so we can finish it up. On the first sensor, seems that the error in the location, which is this crosshair, the error is higher in the x direction, smaller in the y direction. Right? So each sensor measures a location, that mean, right? So the uncertainty is higher in the x direction, smaller in the y direction. The other sensor, the uncertainty, the x is small, in the uncertainty, the y is huge. So when you combine the two sensors together, the posterior basically comes to be this, okay? And effectively this uncertainty, the wrong message is coming, the competing message is coming from the two sensors are counted in this posterior that gives you this cross on the middle. This, of course, you're going to the likelihood model, you're going to have to use likelihood with different variances for each sensor, right? But